Imagine in front of you there is 1 kilogram of steel on one side and 1 kilogram of water on the other. If we add heat to these two objects, in other words, a constant input of energy, we intuitively know that the steel will heat up faster than the water. In fact, if we wanted to raise the temperature from 20 degrees to 30 degrees Celsius, it would take 5 kilojoules of energy for the steel and 41.8 kilojoules of energy for the water. It's good if we have a property that can compare the ability for energy storage in different substances. This is called specific heat. Formally, we can say that specific heat is the energy required to raise the temperature of a unit mass of a substance by 1 degree. There are two different kinds of specific heat that we need to know. There is specific heat at constant volume and specific heat at constant pressure, denoted CV and CP. So as the names say, in one scenario, it's the energy required to raise the temperature of the unit mass of a substance by 1 degree while we maintain the volume to be constant. For CP, it's the same except we hold the pressure constant. Now to hold the pressure constant, the system has to expand, and that expansion requires more energy. So you will notice that CP values will always be greater than CV values. You can find these values on tables like these for all sorts of different substances. The units for it are these, and you should note that this is equivalent to the Celsius version, so you can switch them. Another thing to keep in mind is that CV is related to internal energy of the system, whereas CP is related to the change in enthalpy of the system. You might remember that we talked about the ideal gas equation. Now we're going to relate internal energy to ideal gases. Interestingly, internal energy for an ideal gas is a function of temperature only. In simple terms, it's based only on temperature, regardless of specific volume or pressure. In fact, enthalpy of an ideal gas is also a function of temperature only. Now, since both internal energy and enthalpy of ideal gases are based only on temperature, then specific heat is also dependent on temperature only. There are two equations we need to keep in mind with respect to change in internal energy and enthalpy. For specific internal energy change, we can use this equation. The units would be kilojoules per kilogram. If you don't want it per unit mass, then you simply multiply everything by mass, so you get this. For the change in enthalpy, we can use this equation. Notice that for internal energy change, we use CV, and for enthalpy change, we use CP. Another equation that can be used when it comes to specific heat and ideal gases is this. We can use this to figure out CP or CV, as long as we have one of them and the gas constant. Lastly, there is a property called the specific heat ratio, and it's simply the ratio you get when you divide CP by CV. We talked about polytropic processes before when it comes to moving boundary work. We used this equation to figure out the boundary work in such a process. If the system contains ideal gas, then we can use this equation to figure out the boundary work. Notice that it's actually just an incorporation of the ideal gas equation. The units would be kilojoules. If you need it per unit mass, then you simply find it using this, which would have the units kilojoules per kilogram. Now let's move on to some examples to see how we can use the equations we talked about. To solve these problems, you should be familiar with the ideal gas equation and energy balance. So if you need a refresh, please check the description. Let's take a look at this question where we have an electrical oil radiator in a room. After some time, the room heats up and we need to figure out how long the radiator ran for to warm up the room. Let's write down what we know. The volume of the oil is 40 liters, or 0.04 cubic meters, and the volume of the room is 50 cubic meters. The initial temperature for the room and the oil in the radiator is 10 degrees Celsius. The radiator has a power rating of 2.4 kilowatts or 2.4 kilojoules per second. There is a heat loss in the room, which is 0.35 kilojoules per second. After some time, the temperature of the air is 20 degrees Celsius, and the temperature of the oil in the radiator is 50 degrees Celsius. We're also given the density and the specific heat of the oil. While it's not given, we will also need the gas constant of air, which we can find from this table, and that's the value right here. Also, keep in mind that the local atmospheric pressure is 100 kilopascals. Lastly, we need the specific heat of air at constant volume and we can find that using this table. That's the value right here. Okay, now we can write our energy balance equation. So energy in minus the energy out is equal to the change of energy in the system. Now the heater is on for a certain amount of time, which is our energy in. Because it's on for a certain time period, we need to multiply it by delta T. Now while the heater is on, we're told that there is a heat loss in the room. That's also happening during this process for a certain amount of time. That's our energy out. Now what changes occur in the system? We have two changes. So that's the change of internal energy in the air and the change of internal energy of the oil. No other changes occur in the system since we have no potential or kinetic energy change. Now how do we figure out the change in internal energy of the air? Since we're given the specific heat and there is a change in internal energy, we can use this equation. The same can be applied to internal energy change of the oil. So looking at these two equations, we're given everything except the mass of air and the mass of the oil. First, we will find the mass of the air. To do so, we need to keep in mind that with the parameters given, the air will act as an ideal gas. So let's write down the equation for an ideal gas. Let's isolate it for mass. Now we can plug in the initial values given to us. Don't forget, we need our temperature in Kelvin to use this equation. Let's solve. Now we need to figure out the mass of the oil, which is much easier. Mass is density times volume, and we have both of those values. So let's plug in our values and solve. Now that we have the mass, we can find the internal energy change of the air and oil. We will start with the air. Let's plug in our values. Solving gives us the internal energy change of the air. Next, we move on to the oil. So as before, we plug in our values and solve. Now we can go back to our original equation. Since delta T is common to both terms, we can factor it out like this. Now we can plug in our values. Let's solve, and that is the time it took for the temperature of the room to rise from 10 to 50 degrees Celsius. In this question, we have argon in a piston cylinder device and is compressed in a polytropic process. We need to figure out the work produced and the heat transferred during this process. Let's write down what we know. The N value is 1.2, the initial pressure is 120 kilopascals, and the final pressure is 800 kilopascals. The initial temperature is 10 degrees Celsius or 283.15 Kelvin. Let's also find the gas constant of argon and the specific heat at constant volume for argon. Here are the values we need. Now this is a closed system because mass doesn't leave the system, but boundary work is definitely involved. Keeping that in mind, we have energy in minus the energy out, and that's equal to the energy change of the system. Now we don't know the directions for work and heat transfer, so we're going to assume the normal convention for heat transfer and work transfer. The normal convention is to assume that heat is going into the system and work is done on the system, meaning work output. And that's equal to the change in the internal energy of the system since there is no potential or kinetic energy change. The internal energy change can be found using this equation. Since the question wants us to find the values in kilojoules per kilogram, in other words, per unit mass, we can eliminate mass from the equation and write it per unit mass like this. Looks like we have a bunch of things that we need to figure out. First, we will figure out the initial and final conditions, which include initial specific volume, final specific volume, and final temperature. Given the conditions, argon will behave like an ideal gas, so we can use the ideal gas equation to figure out the initial specific volume. Let's isolate the equation. Now we can plug in our values. Let's solve and we get our initial specific volume. To find the final specific volume, we can use this equation relating the polytropic process. Volume is mass multiplied by specific volume, so let's replace it. Now remember, mass is constant during the whole process since mass doesn't leave the system, so we can eliminate it. Let's plug our values in. Now we can solve for the final specific volume. Next, we need to figure out the final temperature. We can use the ideal gas equation that compares two states. Volume is mass times specific volume, so let's replace it. Going back to what I said, mass is constant, so we can cancel it out. Let's plug in our values. Solving gives us the final temperature. Now we're going to figure out the boundary work. For that, we can use the equation to find boundary work when it comes to a polytropic process and an ideal gas. Note that the question wants us to figure out the work produced in kilojoules per kilogram, which is per unit mass. So we're using the specific volume form, meaning mass isn't required. Let's plug in our values. Since we want our answer in kilojoules per kilogram, we need a unity conversion ratio as well. We get a negative answer, which means that this is actually work input. In other words, we need to input work to compress the gas. To figure out the heat transferred, we go back to our original equation with the energy transfer. Now we can plug in our values. Make sure to plug in the negative value since we wrote our equation assuming work output. Let's solve. We got a negative answer, so that means it's heat output. In other words, heat is transferred out when the gas is compressed. And those are our answers.